Now, the next one that we want to run through is involving nucleophilic sub. Again, let me just give you an overview. What are some of the things that we will run through? The mechanism, again, we will draw on the left-hand side, involving SN1, SN2 mechanism. There are some ideas which we will have to discuss, which are pretty interesting. Stereochemistry, the number of steps, and the rate equation for SN1. SN2, we will do the same thing. We will do this comparison. So mechanism, we put it on the left-hand side. The description, we put it on the right-hand side. Then later, we also want to do a comparison involving the nature of the halide. Different halides will favor SN1, SN2 mechanism, but we will talk about it subsequently. Also, let us consider this first portion here first, involving the why would halogenoalkane undergo nucleophilic substitution reaction. Hopefully, we are getting the hang of it. It's actually quite simple. Based on the charge of my carbon, I can decide whether it reacts with an electrophile or nucleophile. So if I look at my halogenoalkane carbon, which is attached to a halogen, more electronegative, halogen is delta minus charge, carbon is delta plus charge. So if I'm positively charged, then obviously I'll react with a nucleophile, undergo nucleophilic reactions. So if you consider these ideal things like alcohol, carbon attached to more electronegative oxygen, carbonyl compound, carboxylic acids, acid derivatives, where carbon is attached to more electronegative oxygen, all these functional groups will all react with nucleophiles. That's why you notice this idea is important, because once we understand, based on the charge of my carbon, I can decide whether it reacts with E plus or Nu minus. I can extend this to other functional groups. I can apply this to other functional groups. Then type of reaction, halogenoalkane is saturated, so therefore you undergo substitution. So tendency is saturated will undergo substitution, unsaturated will undergo addition reaction. Again, I can use this to predict the reactivity of other functional groups. Okay, the reaction that we'll be doing today is this one. You just keep in mind this carbon is actually chiral, bonded to 4 different groups. So we will be able to talk about the stereochemistry involving this guy. So let us consider the SN1 mechanism first. And the mechanism or the orientation of my halogenoalkane that we'll be using, you try to use what we have here so that we will end up with the same thing. SN1, we know that this is a 2-step reaction, correct? So I draw my CBr bond like that, CH3 on the paper. This is the ethyl group, CH3, CH2 on the paper. CH3, we draw it towards you. Hydrogen, we draw it away from you. So this will be the orientation for my organic compound. Now, SN1 mechanism, we say that this is a 2-step reaction. So the first step is the CX bond will break by itself. So this is my delta plus, delta minus. Draw an arrow from the CX bond to bromine, and this will be the slow step, correct? And I'll end up with a carbocation ion, CH2, CH3 on the paper. CH3 towards you, hydrogen away from you. Now this is a C plus. You form a Br minus. So effectively, this will be my first step, forming a carbocation ion. The second step is this guy is positively charged. The OH minus will come in and whack the C plus, forms the product. So which is pretty simple. The second step, I just need to duplicate this guy, CH2, CH3 on the paper. CH3 towards you, hydrogen away from you. This guy is a plus. OH minus will come in, lone pair on oxygen, point to carbon. So this second step is fast. I'll end up with the product. Now, product-wise, recommendation is you draw it flat. That means we don't show the stereochemistry because the product, it is a racemic mixture. If you draw the 3D bond and if you only draw one of it, then you're only drawing one optical isomer, which technically speaking is not really correct. So one way to represent it, which is simpler, is you draw it flat. So that if you draw it flat, you will mean that it can be a racemic mixture because we are not showing the specific orientation of where the groups are pointing. So you keep this in mind, the product in this case, this is a racemic mixture. And of course, we want to explain why the product will be a racemic mixture. So this will be my SN1 mechanism, which is a 2-step reaction. Not that bad. Again, I think we will be familiar with drawing out the mechanism. It's just some of these notes that we want to run through, which we want to recap. So if you haven't copied the whole thing, doesn't matter. Then the mechanism is still here. We can still copy this down. But what we want to emphasize on is the right-hand side. There are a few ideas that we want to run through. First one, it is the stereochemistry of the product. Why would SN1 mechanism give me a racemic mixture? The reason is because of the nature of my carbocation. It is a trigonal planar. The carbon, it is sp2 carbon. This guy, it is planar. And if it is planar, then it is flat. If it is flat, both sides are equally exposed. So therefore, it can be attacked by the nucleophile from the left-hand side 50% of the time. From the right-hand side, also 50% of the time. So the idea is very simple because this guy is flat, both sides are equally exposed, so the incoming group can attack from both sides to equal proportion. And the consequence is I'll end up with a racemic mixture. My suggestion is to try to draw this one time to convince yourself that if the OH minus comes in from the left, this is the product that I'll get. If it comes in from the right-hand side, this is the product that I'll get. And if the probability of this happening is 50-50, then the product that I'll get is also 50%, 50%. It's actually not very difficult for us to draw if I keep it consistent. Now, this guy is the same intermediate as we have here. ET is the ethyl group, CH2, CH3. ME, it is the methyl group, CH3 group. Again, we try to draw the same orientation as this guy. Ethyl group on top, methyl group towards you, hydrogen away from you. When the OH minus comes in from the left-hand side, this will be the product. OH minus is on the left, ethyl group on the paper, methyl group towards you, hydrogen away from you. All right, 50% from the left-hand side, so you form 50% of this as the product. Now, if it comes in from the right-hand side, the OH minus attacks from the right-hand side, this is the product that we will get. OH minus is on the right, ethyl group is on top, methyl group towards you, hydrogen away from you. So this is the product that I'll end up getting. 50% chance of coming in from the right-hand side, so you form 50% of this as the product. Of course, we notice that these two guys are mirror images of each other. So they're optical isomers of each other, correct? And we know that if they're optical isomers of each other, and you have 50%, 50% of this guy, they will be able to cancel out each other's optical activity. So we call this mixture a racemic mixture. Racemic mixture is optically inactive, cannot rotate plane polarized light. And I think this idea we have to keep in mind because there's another mechanism which will have the same outcome, which is my nucleophilic addition for my carbonyl compound. Based on the same idea, the starting guy, it is flat. Carbonyl compound is trigonal planar, right? The carbon is sp2 hybridized. So if it is flat, same story. If it is flat, both sides equally exposed, can be attacked from both sides to equal extent. The consequence is I'll have a racemic mixture. So this idea, I can extend this to both SN1 mechanism as well as nucleophilic addition reaction. So we have to keep this in mind. Okay, so this is idea number one. Now, idea number two is the number of steps. We know that SN1, it is a two-step reaction. So if I were to draw the energy profile diagram, of course, there will be two mountains to draw. Assuming the reaction is exothermic, I will draw the alcohol lower enthalpy level as compared to the reactant, the halogenoalkane. But I think the enthalpy change for the reaction is not that important. If it is endothermic, of course, we just draw the product higher enthalpy than the reactant. I think that one is not much of an issue. Intermediate-wise, carbocation should be less stable than the rest. So C plus should be above enthalpy level as compared to the reactant and the product. What is more important is the activation energy for the steps. I know that the first step is the slow step, so make sure the first activation energy is higher than the second one. We draw the first activation energy big, second activation energy you must draw it smaller. My preference is to amplify the activation energy for the slow step, make it like super obvious that this guy, it is a slow step, and the first step is slow, so make sure the first activation energy is bigger than the second one, consistent with the mechanism that we have drawn. Now, the rate equation, we also have to keep it consistent with the mechanism that we have drawn. We know that the first step is the slow step, and one halogenoalkane involved in the slow step. So therefore, it will be first order with respect to RBR, zero order with respect to OH minus, because OH minus comes in the fast step. So we know that for SN1 mechanism, the rate is not affected by OH minus concentration. Overall order of this reaction is order 1. That's why we say that this is an SN1 mechanism. Remember, SN1, the number represents the overall order of the reaction, overall order 1 reaction. Some of us will call this unimolecular, but unimolecular, maybe it is a bit abstract. My preference is the number is just the overall order of the reaction. Then in terms of application, it is easier for us to apply. SN2 is overall order 2. SN1 is overall order 1. not the number of steps, but the overall order of the reaction. Then we can link this directly to kinetics, easier for us to apply. Okay? In general, we are interested in these 3 points, the stereochemistry of the product, the number of steps, and the rate equation, because when we talked about SN1, SN2 mechanism, the question can give us information involving any of these things that we have talked about. Maybe they tell you something about the stereochemistry of the product, whether is it optically active or not. And maybe they can tell you the total number of steps for this mechanism. Maybe they can give you a kinetics question, ask you to deduce the rate equation. From there, we figure out whether this is SN1 or SN2, or they can tell you that whether the reaction is affected by OH minus concentration or not affected by OH minus concentration. And then from there, we deduce whether this is SN1 or SN2. So very common, they will give us data. Then based on data, we deduce whether this is SN1 or SN2, and we draw the mechanism accordingly. So that's the reason why we want to talk about some of these points for nucleophilic substitution. Okay, so this is for SN1. Now, how about SN2 mechanism? Same thing, what we want to do is we want to draw out the mechanism. Now, SN2 mechanism, because it is a one-step reaction, so the nucleophile will come in. We will want to draw the nucleophile on the left-hand side. Then straight away, it can attack the carbon from directly behind the CX bond. Then for the halogenoalkane, we draw the same orientation as SN1 mechanism. In terms of comparison, it will be better. So my CH3, CH2 will be on the paper. CH3 will be towards you. Hydrogen will be away from you. So same orientation as the previous case. Comparison will be a bit better. Same thing, the carbon is delta plus, bromine is the delta minus. Remember SN2, it is the backdoor attack. So the nucleophile will attack from directly behind the CX bond, and you break the CBr bond. So this is a backdoor attack, and it has to come in from the back door. So what we cannot do is we cannot draw the OH minus here, and we draw the attack here. If you draw this way, this is not a backdoor attack because the bromine can see the OH minus. It's not counted as a backdoor attack. If you draw in this way, this is a backdoor attack, but it looks a bit ugly because it looks a bit messy. So when we draw SN2 mechanism, it's better for me to put the nucleophile on the left-hand side. Then when you draw arrow pushing, it looks a bit nicer, not so cluttered. So let me remove this guy so that we can continue with the mechanism. Now, usually we will be required to draw the transition state. And the transition state is just to show the bonds that are partially formed and partially broken. So I'm forming this CO bond, which is partially formed, correct? And a CBr bond, which is partially broken. Then the rest of the group, we will just keep the same orientation. The CH2, CH3 will be on the paper. My CH3 will be towards you. Hydrogen will be away from you. And usually the symbol for transition state that we will use is overall charge for the reactant is a minus charge. So I can put a negative sign here. And this will be the transition state. Now for the transition state, the reason why you notice other mechanism, we don't really draw the transition state. How come for SN2 mechanism, we are required to draw the transition state is to emphasize that the OH group, the attacking group, and the carbon and the leaving group, the bromine, they are along the same axis in a straight line, which is to emphasize that the only way I can form this guy is where the OH attacks the carbon from directly behind the CX bond. Only then you can form something like this, correct? So this will be the transition state. After that, we have to show the product. Then my OH minus is on the left-hand side. The rest of the groups will be flipped towards the right-hand side to try to minimize repulsion with my OH minus. So the ethyl group, CH2, CH3, now will be leaning towards the right-hand side. CH3 group is still towards you. So by leaning towards the right-hand side, try to avoid repulsion with my OH. My hydrogen will be away from you, but it is still leaning towards the right-hand side, plus Br minus as the product. So this would be my SN2 mechanism. Again, pretty simple. We just want to appreciate why is there a need for us to draw the transition state, because we want to emphasize that the OH and the carbon and the Br, they are along the same axis, which means that my OH group is attacking the carbon from directly behind the CX bond. And this is a one-step mechanism. Okay, so let us go back and run through some of these ideas involving SN2 mechanism. Now, SN2 mechanism, the mechanism is here, but some points that we want to discuss in comparison with SN1 mechanism. Now, because this is a backdoor attack and 100% of this comes in through the backdoor, there's only one point of entry, so therefore there's only one outcome. This idea is important. The OH minus can only come in from directly behind the CX bond, so therefore, and when it comes in through the back door, there's this inversion. The groups will all be flipped towards the right-hand side. At the beginning, because they want to avoid bromine, all of them, they are leaning towards the left-hand side. Then when the OH minus comes in and takes the position on the left-hand side, everybody will try to avoid the OH minus, flip towards the right-hand side. So the idea is this, what we call inversion, stereochemistry inversion. And you have 100% of this stereochemistry inversion because all the OH minus must come in from directly behind the CX bond. So there's only one point of attack and there's only one outcome. So therefore, there's only one product. And if I have the starting guy, which is optically active, the product will also be optically active because I only form one optical isomer product. If I compare this with SN1 mechanism, because my carbocation is flat, both sides are equally exposed, it can be attacked from both sides to equal extent. So there are two ways of attack. So therefore, there are two outcomes, which happens to be a racemic mixture. This one, there's only one way to attack. So therefore, there's only one outcome. So this one don't have racemic mixture. This will be optically active, correct? Of course, the discussion involving stereochemistry on whether this is optically active or not, it depends on whether the reactant, whether it has a chiral carbon in the first place. If the carbon is non-chiral, then of course, point number one is not so relevant. But of course, it's still good to talk about it so that we can understand. In the case where we have chiral carbon, then we know that SN1 mechanism will give me a racemic mixture. SN2 mechanism will give me a sample, which is optically active. Now, the second point involving the mechanism, this drawing the energy profile diagram, this is a one-step reaction. So therefore, there's only one mountain to climb. You keep in mind the transition state, it is the top of the mountain. And usually for other mechanisms, we don't draw transition state. And we don't want to mistaken this as a two-step mechanism. In my opinion, you notice when I draw the mechanism, I never write down slow step because if this is the only step, then it has to be the rate determining step. It becomes a bit redundant for me to indicate the slow step. But some of us, maybe your tutor want you to write down slow. But if you write down slow here, please don't write down fast here. Because you write down slow fast means it becomes a two-step reaction, which is totally wrong, correct? In my opinion, I think it's not really necessary for me to write down slow. But if you do use that, please don't write down slow fast. You write down the fast, then you're making it into a two-step reaction. Then the idea, of course, will be entirely different. So this will be the mechanism, one-step mechanism. Rate equation, of course, I can get this from the only step, which is the rate determining step. One OH minus involved, first order, with respect to OH minus. One halogenoalkane involved, first order, with respect to halogenoalkane. So you notice now, this will be an overall order 2 reaction. That's why we call this SN2 mechanism, or some of us will refer to this as bimolecular reaction. And the rate now is affected by OH minus concentration. Again, some of this information that we pull out is to try to differentiate between SN1 mechanism versus SN2 mechanism. And we do need to know how to differentiate between these two guys so that if the question gives us data, we can decide whether this is SN1 or SN2. And if you ask me to draw the mechanism, we draw the mechanism accordingly. SN2, it is the backdoor attack. SN1, it is a two-step process involving the formation of our carbocation. So we want to keep this in mind.